This video is covering sections from 10.4 and 10.5, which is just looking at polar basics and just non-calculus questions dealing with polar. I'm just going to do a very brief review of polar just to kind of remind you what it looks like. I'm not going to be doing all the problems on this. I just want to kind of specifically show you what you're going to see on the AP test. All right, so first of all, a review for a point in the polar plane, which you see here is the polar graph, can be assigned the polar coordinate r theta. Now, when we think of r theta, it's kind of the opposite of xy, where x is the independent and then y is the dependent. Well, theta is actually the independent variable and r is the dependent variable. So when we have equations, instead of like y equals in terms of x, we have r equals in terms of theta typically. Now, that gets confusing because of the order. The theta doesn't come first like the x does, and that's simply because of alphabetical order. So the r comes first because r comes before the th, which is the theta, the Greek letter for th, and that's why it's ordered that way. But know that theta is independent and r is dependent. All right, so r is the directed distance from the pole, in other words, the radius. Just a quick review here, the pole is just the center, it's just the origin. And then the radius has a directed distance because it could be both positive or negative. And theta is the directed angle, just like when we measure using the unit circle. All right, so just a review with plotting points. So if I want to plot the point 2, 5 pi over 6, that means a radius of 2 at the angle of 5 pi over 6. So 5 pi over 6 is here. And so if we go from the pole and we go 1, 2 steps away from the pole, then my point is right here. And it's not a line, it's just a point. So that is point A there. Okay. Then we have the point 3, negative pi over 3. Well, negative pi over 3 would go in the opposite direction. So negative pi over 3 is the same as 5 pi over 3. And then we have a radius coming from the pole in that direction that has a length of 3. So that is point B. And then point C, notice we have a negative radius at pi over 4. So at pi over 4, which is here, the point here would be positive 3 pi over 4. But since it's negative, what we're going to do is we're just going to flip across on the opposite side and put a point at 3 across on the negative side of pi over 4. And that is the point for C. Okay, so that was just kind of a brief preview on how we graph polar coordinates. Now, just a reminder that each rectangular coordinate is unique. That means every point is its own point and you cannot represent it a different way. But this is not the case with polar coordinates. There are an infinite number of coordinates to represent each point because we go around and around, so you can just keep adding 2 pi or you do negative radii or things like that. Also, the pole we talked about was the center, but the pole can be represented by the point 0 theta because it does not matter what theta, what angle you're at. If you have 0 radius, then you will be at the pole. All right, so I'm going to skip over the next few examples. This is just talking about converting from polar to rectangular and vice versa. The next page, also converting equations back and forth, but I'm going to skip to the next page, which is points of intersection of polar graphs. All right, so when we find points of intersection of rectangular graphs, we would just set the two equations equal to each other, which is what we're going to do with the polar. So if we want to find where these two polar equations intersect, we're just going to set them equal to each other. So 1 minus 2 cosine theta equals 1, and then solve. When you subtract 1, you get 0. It doesn't matter that you have the negative 2, so you're just going to look for when cosine theta equals 0. Typically, if unless otherwise stated, we're going to go from 0 to 2 pi. So cosine of theta equals 0 at pi over 2 and 3 pi over 2. Okay, so now those are the thetas, but it asks to find the point of intersection, so we need to find the r's with it. Now, this is a nice one because r equals 1. So if and r equals 1, by the way, is a circle of radius 1 centered at 0. So this is actually, r equals 1 is just the unit circle. So if this other polar graph intersects the unit circle, then what would the radius be? 1. Okay, so that's really easy. Now, if you didn't have a circle of a constant radius, then you could just plug in theta into one of your equations and solve for r that way. Okay, so these points of intersection would be 1 pi over 2 and 1 3 pi over 2. All right, however, to find points of intersection with the polar graph, that is not enough. Okay, without a calculator or without a graph, that's all you could really find. However, you could have more points of intersection than what you find that way. Because of the angle measurement and when it passes through the graph. So if you will, go ahead and get out your calculators. We're going to use our calculators, so I want you to get used to using that. So get out your calculator and go to a graph and change the mode to polar. Then go ahead and put in these two graphs, 1 minus 2 cosine theta and r equals 1. Go ahead and do that. Okay, here are the graphs of 1 minus 2 cosine theta and r equals 1. Now notice that we found the points of intersection to be at 1 pi over 2 and 1 3 pi over 2. So if you notice on this unit circle, pi over 2 would be right here. So that would be the point 1 pi over 2, and then 3 pi over 2 would be down here. So there's that point of intersection. Okay, but however, you can see right here is another point of intersection. So we're not able to find both of them. Now the reason that this does not show up is, like I said, is like when that crosses through. So pi over 2 and 3 pi over 2, what's happening at those points is if there was a point like running along this curve, then at that exact theta, those 2 points were going to collide on those graphs. But at this point over here, it's like on the red one, it passes through at a certain point, and on the blue one, it passes through at a different time. So they're points of intersection, but not simultaneous points. So if I trace the graph, I want to show you why. If I trace this graph with the blue graph, you see that my radius is -1 here at 0 radians. So we're at 0, right, which would be, theta would be on the positive x-axis, but then with a radius of -1, so that's why it's on the negative part of the x-axis. So you see that on the blue graph, this point is occurring at -1, 0. However, if I switch to the red graph, then at that same point, we're now with a radius of 1, but at pi. So at theta 0, that red graph is over here, and then it goes through like the unit circle does. At pi, it now has a radius of 1. So you can see that these two go through the same point, but at different thetas, okay? But if I were to follow my curve along, and then hit that 3 pi over 2 mark, then you can see that those are roughly happening at the same time. Okay? Okay, so just to reiterate, your points of intersection are everywhere the paths cross. So for that example, we actually had 3 points of intersection. So as we already talked about, not all points of intersection will show up by solving algebraically. This problem does not occur in rectangular systems because there's no time involved, no theta involved, just the picture. But in polar coordinates, there are multiple ways to represent a single point. But then we have simultaneous solutions. Now, we can calculate simultaneous solutions algebraically, and that's what we just calculated for this example. So for that one, we would have had those 2 places where the particles would crash. Okay? Now, without a calculator or a graph, okay, and remember, you do not have to memorize these graphs for the AP test. You would only be able to find those simultaneous solutions. However, there is one other point that you could check, and that is the pole. Because the pole is represented by 0 theta, where theta is any angle, you can separately check, and you actually must separately check, to see if the pole is a point of intersection for both graphs. So all you have to do is just plug in r equals 0 for your equation and see if you get a value for theta. Now, this example, the pole was not an intersection point. If you look at the graph, you see the pole is not an intersection point. The blue graph goes through the pole, but the red graph does not. The reason being is For my blue graph, r equals 1 minus 2 cosine of theta. You would have a value of theta for which that radius would equal 0. However, r equals 1, you can't make r equal 0 because 0 doesn't equal 1. Okay, so that one, the pole is not an issue. All right, so let's try the next example then. We want to find all points of intersection for r plus cosine theta and 1 plus cosine theta and 1 minus sine theta. Now, without a calculator or graph, you can only find the simultaneous solutions and the pole, and that's all we're going to do. So we're just going to do the algebraic method here. All right, so to find the simultaneous solutions, so I'm going to kind of change that to simultaneous solutions and pole. Okay, now again, if you had a calculator or if they gave you the graph, you'd have to do more. All right, so we're going to set these two equal to each other and solve. All right, now the ones are going to actually cancel out, so you're left with cosine theta equals negative sine theta. I would actually stop there and think about when is cosine equal to the opposite of sine. That should be pretty easy to remember. Cosine is the same as sine at pi over 4. So when they're the opposites are going to be at 3 pi over 4, which is in the second quadrant, and also in the fourth quadrant, which is 7 pi over 4. Okay? So if I wanted to find, again, we're finding the points of intersection, so we need to find those radius. So all you have to do is plug that back into one of the equations, doesn't matter which, and solve. So I'm just going to use the cosine one. So 1 plus cosine of 3 pi over 4 would be 3 pi over 4, that'd be the second quadrant, so that'd be minus root 2 over 2. And then the other one at 7 pi over 4, now cosine, that would be positive root 2 over 2. So our point of simultaneous points are going to be 1 minus root 2 over 2, 3 pi over 4, and 1 plus root 2 over 2, 7 pi over 4. All right, so those are our simultaneous solutions, but you have to also check for the pole. So to check for the pole, all you have to do is set each of your equations, or set r equal to 0. And just see if you get a theta. They do not have to be the same theta because they don't have to go through at the same time. All right, so when will cosine theta equal negative 1? That will occur at pi. And then when will sine of theta equal positive 1? That will occur at pi over 2. So since both of these will cross through the pole, that means the pole is a point of intersection. Okay, not simultaneous, but it is a point of intersection. All right, so that's it for this video. The next video, we're going to look at derivatives and polar equations.